Beam, jam, burn: how EW and lasers will break drone swarms. 200 low-cost quadcopters lift from a tree line at dusk, skimming the rough ground where radar has blind spots and infrared sees too many hot rocks. Their control links hop across unlicensed bands. Some fly line of sight to a relay, others fall back to onboard autonomy when the spectrum turns hostile. On the perimeter berm, a mast of sensors snaps to life. Radio frequency detectors paint the air, electro-optical trackers lock onto glints, and the command node must decide in seconds which effect to unleash. Do you flood the spectrum to shear the swarm's coordination? Do you pour photons onto the leaders? The choice isn't academic, it's survival at the speed of software. Swarms flip the cost exchange. The attacker buys mass for hundreds of dollars per airframe and scales by pressing build again. The defender, if stuck in a missile-only mindset, spends 5 figures a shot and runs out of magazine depth long before the raid runs out of drones. Human decision cycles can't task individual targets fast enough. Sensors saturate, timelines compress, and good enough automation becomes the difference between managing a raid and being managed by it. The answer is not a single silver bullet, but a layered, electric magazine that treats electrons and photons as primary weapons. This is the playbook: beam, jam, burn. First, use beams, your sensing and steering, to find, classify, and shape the raid, and, when available, to project wide-area, high-power microwave effects that upset entire clusters. Then jam: electronic warfare, EW, to deny control links, spoof navigation, and fracture the swarm's cohesion so autonomy stumbles. Finally, burn: high-energy lasers to deliver precise, low-cost kills on what leaks through. Soft kill first, hard kill last. Automate assignment by cost, probability of kill, and time. What follows turns that mantra into a practical defense you can actually field. Why swarms are hard. Defending against a drone swarm starts with the problem of saturation. A radar that comfortably tracks a dozen fast jets may suddenly face hundreds of small, low-flying objects with erratic flight paths. Human operators are quickly overwhelmed by the sheer volume of tracks on their screens, and even automated systems must be tuned to distinguish real threats from clutter, like birds or debris. This density is intentional. It aims to overload the defender's decision cycle and create gaps where attackers slip through. Another challenge is resilience built into swarm design. Some drones rely on continuous uplink guidance. Others operate with pre-programmed waypoints, and still others communicate laterally in a mesh network. If one layer of control is disrupted, another can sustain the mission. This redundancy makes the swarm resistant to single-point failures. Even partial losses don't neutralize the attack. Dozens of surviving drones may still succeed in damaging a target. The problem is compounded by spectral agility. Many small drones are programmed to hop across multiple frequencies, employ spread spectrum signals, or shift to low probability of intercept waveforms. Others can abandon radio entirely and switch to optical or infrared communication. Defenses that rely on static jamming techniques find themselves chasing ghosts, while the swarm adapts on the fly. This flexibility in the electromagnetic spectrum forces defenders to field equally adaptive countermeasures. The most punishing factor is the economics of attack versus defense. A quadcopter equipped with explosives or cameras can be manufactured or purchased for under $1,000. Defenders often respond with interceptors or missiles that cost tens or hundreds of thousands of dollars per shot. When the attacker can generate mass at low cost and the defender burns through an expensive inventory, the imbalance becomes unsustainable. This is why electronic and directed energy approaches, scalable, reusable, and relatively inexpensive per engagement, are drawing so much attention. Defender's kill chain for swarms: find, fix, track, target, engage, assess. Countering swarms requires treating each engagement as a kill chain, a disciplined process that begins with discovery. Find relies on fusing multiple sensors to create a picture of the battle space, radar for range and velocity, infrared to pick out heat signatures, electro-optical systems for visual confirmation, and RF sensing to intercept control signals. No single sensor can provide full coverage, but their integration allows defenders to detect drones that would otherwise evade notice. The next steps: fix and track. Focus on pinning down the swarm's behavior. It is not enough to know drones are present. Defenders must understand where they are going, how fast, and which ones pose the greatest threat. Automated tracking systems help categorize targets by intent separating reconnaissance drones, loitering at the edges from those diving toward critical infrastructure. This tiered awareness enables scarce defensive resources to be directed where they matter most. The target and engage phases determine which countermeasure is applied to which threat. Electronic warfare and high-power microwave systems are best suited for wide-area disruption against clustered drones. Lasers or interceptors are reserved for stragglers or priority targets. Assigning the right tool requires balancing speed, cost, and probability of kill, all under conditions where decisions must be made in seconds. Without automation, human operators alone cannot keep pace with a raid's tempo. Assessment closes the loop. After each engagement, the system must verify whether the effect succeeded. A drone forced into autonomy may continue flying, while another that loses navigation may veer off harmlessly. Continuous assessment feeds back into the chain, allowing defenses to shift tactics dynamically. If a jammer proves ineffective against certain frequencies, those drones are reassigned to the laser queue. This iterative cycle ensures defenders can adapt at the same speed the swarm itself evolves. Beam, sensing and amp, high-power microwaves, HPM. The concept of the beam begins with sensing. Electronically steered radar arrays and optical tracking beams allow defenders to locate, classify, and track hundreds of drones simultaneously. Unlike older mechanical systems, these arrays can shift focus instantly, jumping from one cluster to another without delay. The ability to rapidly retask beams ensures that defenders keep pace with swarms that maneuver in unpredictable patterns, turning the act of sensing itself into an active part of the defense. Beyond tracking, beams are also tools for engagement through high-power microwaves, HPM. These wide-area electromagnetic pulses can upset or permanently damage the electronic components inside multiple drones at once. Rather than requiring a pinpoint aim point like a laser, HPM spreads energy across a cone, making it effective against dense raid formations. This capability is particularly useful in early engagement, where thinning out a swarm quickly provides breathing room for more precise follow-up systems. The effectiveness of HPM lies in its scalability. A single pulse can affect dozens of airframes if they are within the cone of effect, multiplying the defender's efficiency compared to one-for-one interceptors. HPM also offers an infinite magazine as long as power is available, which is crucial during sustained raids. This combination of breadth and repeatability makes it a cornerstone for defending large fixed sites or massed formations in the field. At the same time, HPM comes with constraints. Its line-of-sight requirement limits use in urban terrain or mountainous regions. Power generation and cooling become serious engineering challenges, especially on mobile platforms. There is also the risk of collateral electromagnetic effects, where friendly systems or civilian infrastructure may be disrupted alongside hostile drones. For these reasons, HPM is often positioned as a layer in the broader architecture, not a standalone solution. JAM, Electronic Warfare Playbook: Deny, Degrade, Deceive. Electronic warfare remains one of the most versatile tools against swarms because it directly attacks their links and navigation. Denial of command and control uplinks forces drones into fallback modes that are often less efficient or predictable. Cutting down links prevents operators from receiving video feeds, stripping away situational awareness. Even partial jamming can reduce coordination within the swarm, creating confusion that buys defenders time. Targeting a swarm's dependence on position, navigation, and timing, PNT, is equally effective. Jamming GPS signals can cause drones to drift off course, while spoofing them can redirect formations entirely. A group of drones expecting to converge on a defended site may suddenly veer off toward empty ground. Precision PNT attacks can be tailored so that some drones are merely delayed, while others are completely diverted, fracturing the timing that makes swarms dangerous in the first place. More advanced techniques move beyond denial into deception. Digital radio frequency memory (DRFM) systems can capture an enemy's signal and rebroadcast it with subtle changes, tricking drones into responding to false cues. Instead of a blunt wall of noise, deception allows defenders to mislead swarms into scattering or converging in unhelpful ways. This sophistication increases the defender's efficiency by causing the swarm to undermine itself, rather than absorbing continuous jamming energy. Managing jamming, however, is a balancing act. Friendly communications and sensors share the same spectrum, and indiscriminate jamming risks fratricide in the electromagnetic domain. Frequency-agile drones that hop or mesh around blocked channels also force defenders to keep adapting in real time. Effective EW campaigns require careful planning, adaptive software-defined radios, and strict rules of engagement to ensure defenders don't blind themselves while fighting the swarm. Burn high-energy lasers, HEL, for precision kills. High-energy lasers bring the ability to deliver surgical, repeatable effects against drones at the speed of light. Unlike missiles or guns, a laser can be fired as long as sufficient power is available, making it attractive for sustained engagements. Precision targeting allows operators to disable critical components, optical sensors, control surfaces, or propulsion systems, without needing to destroy the entire airframe. This makes lasers ideal for picking off high-value drones that slip through earlier defensive layers. The challenge of laser weapons lies in their aim point and dwell requirements. To achieve a kill, the beam must remain steadily focused on a vulnerable spot long enough to deposit sufficient energy. This requires advanced optics, jitter control, and thermal management. Against maneuvering drones, maintaining dwell can be demanding, particularly when dealing with dozens of simultaneous targets. Success depends not only on raw power output, but also on software that optimizes targeting and timing. Environmental conditions impose further limits. Weather, dust, and obscurance all degrade beam quality, reducing effective range and increasing engagement times. In desert or maritime environments, haze and salt particles can scatter energy, while rain and fog present natural shields. This sensitivity to atmospheric conditions means lasers cannot be the sole layer of defense. They must be integrated into a broader architecture where other systems compensate when visibility is poor. Despite these challenges, lasers deliver unmatched economics per shot. Each engagement costs little more than the electricity consumed, in stark contrast to the thousands or tens of thousands spent on kinetic interceptors. This makes them particularly well-suited for long-duration raids where magazine depth is crucial. By treating lasers as the precision cleanup tool of the defense stack, commanders preserve their missiles and guns for the hardest, most resilient threats. Layered architecture, how the pieces fit. The most effective counter-swarm strategy is a layered defense, where each system contributes at the stage where it is strongest. At the outer perimeter, passive sensors and RF detection establish early warning. Electronic warfare and deception are employed first, scattering formations and stripping away control links. By thinning the raid before it arrives in range of physical defenses, the overall burden on the system is reduced. In the middle layer, high-power microwave systems come into play. Their wide area effects collapse clusters of drones, forcing survivors into less organized approaches. Because HPM can affect many targets simultaneously, it acts as a multiplier, reducing the number of threats that must be handled individually. This ensures the inner layers of defense are not overwhelmed by mass. Closer in, lasers provide precision firepower, targeting the drones that survive EW and HPM effects. Their low cost per shot allows defenders to engage large numbers without depleting expensive munitions. Guns and missiles remain as the final safeguard, reserved for drones that are hardened, laser-resistant, or otherwise able to press the attack despite prior disruption. This tiered structure ensures that no single defensive element must carry the fight alone. Tying the layers together is the command and control brain. Automated resource managers evaluate each drone, matching targets to weapons based on cost, kill probability, and available time. By automating assignments, the system can act faster than human operators could manage, keeping tempo with the swarm. This orchestration ensures that every watt of power, every burst of jamming, and every pulse of laser energy is applied where it matters most. The math of fire and amp. Power. Every counter-swarm architecture lives or dies by its throughput math, the number of drones that can be neutralized per minute compared to the number arriving. If a defender can only kill 10 per minute, but 20 arrive in the same time window, the system is quickly saturated. This is why wide area disruption, like jamming and HPM, comes first. They thin the raid across many targets simultaneously, reducing the per-minute load on precision systems like lasers or interceptors. Power budgets drive these calculations as much as weapon performance. A laser battery might produce hundreds of kilowatts in theory, but only if the platform can supply that energy continuously. Generators, fuel lines, and thermal management systems often become the limiting factor. The same applies to HPM, where capacitors must recharge between pulses, dictating how many cones of energy can be fired in a given interval. Energy logistics, not just hardware, set the ceiling for effectiveness. Magazine depth is another dimension of this math. Lasers and jammers, so long as they are powered, offer a kind of electrical magazine, reusable and replenishable. Kinetic weapons, however, deplete quickly and require resupply. Commanders must balance these resources, using renewable effects as the first line and saving finite munitions for the toughest targets. The interplay between power availability and munition count is central to sustaining defense through a long raid. The final calculation is about cost exchange. A defender who spends hundreds of thousands to stop a swarm of cheap quadcopters has already lost strategically, even if tactically successful. By leaning on reusable energy-based systems, defenders invert this math-spending dollars to counter adversaries who spent thousands. This inversion is the ultimate goal of beam, jam, and burn, a defense that scales as cheaply and quickly as the threat itself. Conclusion: drone swarms represent the future of low-cost mass in warfare, but they are not unstoppable. By combining beams for sensing and wide-area effects, jamming for disruption and deception, and lasers for precision kills, defenders can build layered systems that neutralize the advantage of numbers. Success depends not on a single silver bullet, but on orchestrating multiple technologies into a cohesive defense. The race now is to scale these systems, integrate them with automation, and refine doctrine so that they can keep pace with swarms in the real world. Power, spectrum, and cost math will decide who wins. In the end, it is not just about shooting drones from the sky, it is about shaping the battle space so that mass loses its advantage and defense regains the initiative.